Greetings, my name is Yuan-Hao Lee. In this video, I'm going to give a brief introduction to our paper, a pixel-level meta-learner for weakly supervised few-shot semantic segmentation. Firstly, semantic segmentation is the task of predicting pixel-wise labels of a given image. This is substantially more difficult than a normal classification task, which requires only one label for a single image. In fact, training a segmentation model itself is not exactly difficult, but obtaining the large amount of ground truth labels required to train such models is very difficult. Recently, the technique of few-shot learning has been applied to the task of semantic segmentation, with many works using the episodic meta-learning scheme to leverage information from base categories at training stage, so that at testing stage, the model can adapt to novel categories with only a few pair of data with ground truth labels. But even with such techniques, we still need a lot of pixel-level ground truths from the base categories. So, we want to further eliminate the need of any pixel-level label at all. Instead of using the pixel-level mask as the ground truth for training, we want to instead use only image-level labels. This means that for each image, we only need the information of what categories are present in this image. So, a summary of the two problems that we solve in this work. First, because deep segmentation models require many training data that are difficult to obtain, we use few-shot segmentation techniques to alleviate this need. Second, because few-shot segmentation still requires ground truth pairs from base categories, we seek to use only image-level label as supervision. Our proposed method can be divided into two parts. In the first stage, because we are training with only image-level labels, we would need to generate pseudo-pixel-level masks. We utilize classification activation maps, also known as CAM, to obtain relevant regions for each category, and perform semantic comparison between the label C and all categories from CAM. The resulting similarity weights are then used to aggregate the CAM heat maps. Finally, saliency gating is applied to reduce false positive regions. The second phase consists of our pixel-level meta-learning framework. Following the episodic training scheme, we sample support and query sets at each episode. The input image and its image-level labels are fed into our pseudo-label generation model, resulting in pseudo-masks M tilde. We use our backbone network dblat v3+ to extract pixel-level features of the input images. Here we note that the backbone is trained with irrelevant categories, which means that both base and novel categories are excluded from the backbone's training dataset. Next, we label the extracted features with our generated pseudo-masks, and for the support set pixel features, we map them into a latent space via an encoder E. For each category, we calculate their prototypes by taking the mean of all encoded pixel features from that category. The query pixel features are also encoded via the same encoder E, and our meta-learning loss function is defined by the sum of distance in the latent space between the support prototypes and query pixel features of the same category. This is also commonly known as the prototypical loss. At inference, we fix the encoder and perform k-nearest neighbor search for each pixel feature, resulting in the final pixel-level prediction M hat. Here are the mean IOU results of conventional n-way k-shot segmentation on two common datasets. The green shaded results are trained under the fully supervised setting, while the red shaded results are trained with only weak supervision. The delta value is the difference between two settings, which is the lower the better. As shown in the table, our model achieves satisfactory performances under fully supervised settings, yet performs favorably against state-of-the-art methods under weakly supervised settings. Here are some one-way one-shot segmentation results. Despite providing our model with partially labeled pseudo-masks as support set ground truths, which are shown in the second column, it is still able to predict masks for query images with satisfactory performances, as evident in columns 4 and 6. For ablation studies, we implement a baseline version without the encoder E. The result is then severely degraded as shown in the first row of the table, meaning that the meta-learning process is indeed the reason for the strong performance of our model. Additionally, we provide results that are trained using pseudo-masks generated without saliency gating. As shown in the second row, only a slight decrease in mean IOU was observed, and it still outperforms the baseline version by a large margin, which means that the use of saliency gating would be preferable but not critical. We summarize our work as follows. First, we propose a novel setting of weakly supervised semantic segmentation requiring only image-level labels. Second, we design a pseudo-pixel-level label generator that leverages both visual and semantic information. Lastly, our meta-learning segmentation framework can predict satisfactory results on novel categories using the generated pseudo-labels. This concludes my presentation. Thanks for listening.